Greetings guys, this is Magnanimous Minds Lectures Online. Today we are treating an engineering science test 1 question paper which was written on the 4th of October 2019. It has 3 questions. Question 1, it's about moments. Question 1.1 says a beam is 1000 centimeters long. Support A is positioned at the left end of the beam and support B is positioned at the right end of the beam. A point load of 100 kg is placed at point A. Another point load of 200 kg is placed in the middle of the beam. Finally, a uniformly distributed load of 5 newtons per meter is placed over a distance of 5000 millimeters from the right hand support. 1.1.1 says draw the loading diagram. 1.1.2 calculate the value of the reactions at the supports. 1.1.3 draw a shear force diagram according to a suitable scale. Show all the main values on the diagram. 1.1.4 indicate from the shear force diagram the values of the maximum and the minimum shear force. So let's attempt to answer these questions. One point one. We are told that the beam is 1000 centimeters long, and then it's much better to convert all these lengths to meters, since others are in millimeters. The other is in millimeters and the other is in centimeters. So 1000 centimeters is equals to 1000 times 10 to the power negative 2 meters, which when we punch into the calculator, times 10 to the power negative 2 becomes 10 meters. This is the length of the beam. And then we've got 5000 millimeters. 5000 times 10 to the power negative 3 equals to 5 meters. Length of uniformly distributed load, UDL. Then we start drawing our we start drawing our beam, whereby we'll use a scale of 1 centimeter equals to 1 meter. So it's going to be from 0 to 10, and then 5 meters, 0 meters. And then we are told that at support A, which is at the left hand side, so we draw support A here. There is the reaction at support A, and then we've got support B at the right end of the beam. The reaction at support B, there it is, B, and here it's and then a point load of 100 kilograms is placed at point A. Then we've got a load which we know that it will act downwards, since weight acts downwards, whereby it will be 100 times 9.8, converting it to newtons. And then we are also told another point load is placed in the middle, of which this one is 200 kilograms. It's 200 times 9.8, converting it to newtons, and we get something. And lastly, we are told a uniformly distributed load is placed over a distance of 5000 millimeters, which is 5 meters, from the right hand side. The right hand side is this side, and then 5 meters it's here, since it's the middle of the beam. So we draw that uniformly distributed load, which will be something like this. Of 5 newtons per meter. This is a reaction A, this is a reaction B. So this is our beam, and then 1.1.2 says calculate the values of the reaction. So to calculate the values of the reaction, we'll see moments about, or firstly we'll have to convert this UDL to a point force, and when we do that we'll end up with something like this. 10 point E, we've got force and a reaction E, and then at the middle we've got what we call a point force, and here we've got a reaction RB. Oh, and I forgot to draw write down the lengths here. So there's 5 meter, there's 5 meter, and then in total this is 10 meter long. Okay, then here our force is going to be 100 times 9.8 is 980. And here is 200 times 9.8, 1960 newtons. Then here it's reaction B, reaction A. Then to change this UDL to a point load, we multiply this by the length, which is 5. So it's going to be 5 newton meter times 5 newtons per meter times 5 meters. So this meter is going to cancel this meter, and we are left with just newtons, which will be 25. And this force acts like at the center of the length whereby the UDL acts. So since this UDL acts like for 5 meters from the right hand side towards the center of the beam, that means the point force due to this UDL, it's going to act at the middle of that length whereby it acts. So it's going to be 5 divided by 2, which will be 2.5. So that UDL acts here, and we'll have this length as 2.5 and this as 2.5, and then this will be 5 meters. There's 2.5 meters, 2.5 meters, and the value of this point load is 25 newtons. So when we calculate the reactions, we're going to say moments about point A equals to 0, since this beam is in equilibrium. So after doing that, and we know that moment equals to force times distance, so we are going to, and this distance is the perpendicular distance perpendicular to the force. That means if we consider this force is the distance from here to here, that's perpendicular to this force. If maybe this force is acting at an angle, we use the vertical, let's say this force is acting at an angle, we use the vertical component times the distance perpendicular to the vertical component. So let's set up our equilibrium equation for the moment about point A. It's going to be, and we know that moments that causes the beam to rotate clockwise are negative, and anti-clockwise it's positive. So with this one, it causes the beam to rotate clockwise. So it's going to be negative the force, which is 1960 times the distance, which is 5, and another negative due to this force. It's going to be negative 25 times the distance, 5 meter plus 2.5, which is 7.5 meter. Then the reaction, which is causing the beam to rotate anti-clockwise, which will be positive. It's going to be RB times 10 equals to 0. Therefore, RB equals to, we add this, take it to the other side, it's going to become positive. So it's going to be negative 1960 times 5 minus 25 times 7.5. Put this in brackets. And then this is what we get. Take it to the other side. It's going to be 9987.5 divided by 10, which comes from here, and we get RB equals to, and that's by 10, it's going to be 998.75 newtons. It's positive because this is negative, this side we take to the other side becomes positive. Then to get RA, we're going to say forces in the y direction equals to 0. The forces in the y direction, we've got negative 980 plus RA minus 1960 minus 25 plus RB, which is 998.75 equals to 0. Leave RA this side, making it subject to the formula, equals to, take everything to the other side. It's going to be negative 998.75 plus 25 plus 1960 plus 980, which will give us 1966.25. That's it for question 1.1.2. Then question 1.3 says draw the shear force diagram. The shear force diagram is of the same length as the beam, whereby sort of a Cartesian plane, whereby the x-axis is the length of the beam and the y-axis is the value of the shear force. So it's going to be from 0 to 10, and then we determine like the length of our y-axis by the forces acting in the y direction, whereby we've got a force at A, another one at the middle, and then the other one is the point force due to the UDL, and the other one is RB. Then at point A we've got two forces, one acting downwards and the other one acting upwards, whereby we have to determine the final value. To do that, we add the two. This one is negative, it's going to be negative 980 plus 1966.25, and if we do that, it's going to be 1966.25 minus 980, we get 986.25. So that will be the length that determines the length of our y-axis. We can put it at 1000, and we'll go by the ratio of 1 centimeter equals to 200 newtons. So let's draw that. 1 2, 3, 4, 5. Okay, then there's the force in newtons. So we've got 1000 here, 800 there, 600, 400, 200, and 0. And the same in the negative direction. 200, 400, 600, 800, 1000, negative 200, negative 400, negative 600, negative 800, negative 1000. The length this side will only highlight the most important part, which is the middle 5 millimeters, and also 7.5 meters. Oh, it's 5 meters, not millimeters. So it's going to be 5, 7.5, and 10 there. So at point A, we have two forces, one acting downwards and one acting upwards. We add them using their signs, whereby the one acting downwards will be negative, and we end up with 986.25. Let's see, that's somewhere here. And then from that point up until the middle, there's no other force acting, so it will just be constant from here up until the middle. And then at the middle, we've got a force acting downwards, which is 1960. So we subtract that, since it's acting in the negative direction. It's going to be negative 1960, and we get negative 973.75, and that's going to be somewhere around here. Negative it's going to be negative 97. Yeah, it's going to be around here. So that means this shear force is going to come down like this to that point. And then from there, we've got a UDL that's acting from this point up until the end. And that UDL, it's actually it becomes a point force of 25 newtons. So we subtract 25 newtons from this, and we mark that point at the end. So that's the influence it has. That's what it does, like to, let's see, our 1000 somewhere here, so that this can make sense. It should be proportional. So the impact or the influence that the UDL has is 25 newtons throughout this length. So we subtract the 25 newtons and mark it at the end of where the UDL acts. Then from there, that's when we will draw a line from this point to that point. So to do that, we'll sort of mark this end, and we subtract 25 newtons from this point, which is negative 973.73. That's 25. It becomes negative 998.75. Negative 998.75. It's somewhere here, close to 1000, and we draw that line, which is not a straight line. It's not a which is not a horizontal. It's a bit skewed going downwards. It's a straight line with a gradient that's going that way. It's not horizontal. It's not parallel to the x-axis. Let me say that. It's not parallel to the x-axis. It's a bit skewed downwards. And then from there, we've got a reaction at B, which is 998.75, going towards the positive direction. Then if we add that from this, which is negative 998.75 plus 98.75, we get 0, and 0 it's right here. Then we draw the line to complete our shear force diagram. Then when we do that, it's complete and it's correct, since the body is in equilibrium, and at the end we get a shear force diagram that shows us that the body is in equilibrium, because it starts from somewhere here going up there, then comes down here, goes down and comes back to 0, to show that the resultant it's 0. And then question 1.1.4 says, indicate from the shear force diagram the maximum and minimum. So the maximum will be at this point. Although it's negative, it's going to be maximum value, since f equals to 998.75 negative 1, and this will be the minimum value, since f equals to 166.25 minus 80. It's 986.25 newtons. And we are done with question 1.